Okay, everyone, we finally have this working. So, we're very happy to have Professor Rafal Dunin-Borkowski from Jülich telling us about atomic resolution transmission electron microscopy. Thank you very much.
Okay, thank you, Nabil. And now we switch subjects about as far as it's possible to switch from one topic to another one. We go from cosmological length scales down to the atomic scale, and specifically transmission electron microscopy. My slides will be maybe I'll hold this. Is that better? Yeah? Okay. So my slides will only contain a small number of pages of equations. They will be much more conceptual in nature, and I'll try to explain why electron microscopy is a challenging subject to describe phenomena in analytically, why very often numerical descriptions are required. But I'll also try to illustrate what kind of observations are possible, what they tell us, and how it links to different disciplines in physics. But just to begin with, I'd like to start off by going through what length scales we will be discussing. Now, because we are looking on the atomic scale, we are interested in typical sizes of atoms and typical interatomic distances. And those distances are on the order of 1 to 2 angstroms, in other words, 0.1 to 0.2 nanometers. Now, there are a number of different techniques which are capable of obtaining information about materials on that length scale. You can use various types of radiation. You can use X-rays. You can use neutrons. You can use scanning probe techniques, atomic force microscopy, scanning tunneling microscopy. And in our case, we use high-energy electrons. And by high energy, what I mean is electrons which have been accelerated by voltages of somewhere between 50,000 volts and 500,000 volts. This means these are electrons which have been accelerated to somewhere between about 50% and 80% of the speed of light. And we look at these and we use relativistic electrons to look at the atomic scale properties of materials. Now, the electrons that we use have wavelengths on the picometer scale, typically somewhere between 1 and 3 picometers. In other words, much smaller than atomic scale dimensions. And one of the questions I'd like to address during this talk is why using electrons which have a wavelength that's some 100 times smaller than a typical atomic dimension doesn't in practice give us information on the subatomic scale, and what information high-energy electrons really provide us with. So first of all, just to set the scene, I'll start off with a picture of the typical type of instrument that we use to record typically images or sometimes diffraction patterns, sometimes chemically sensitive spectra of materials. I'll assume that you know very little about or nothing about electron microscopy, so I'll start off right from the very basics. So conceptually, a transmission electron microscope is in some ways like a light microscope. As the word transmission suggests, we transmit electrons through a sample, a material, and it's like a large slide projector in some ways, except that we use electrons which are traveling, as I mentioned, somewhere above half the speed of light. They are traveling down from a heated filament or a field emitter, which is normally located at the top of the microscope column. The sample that we look at is located about halfway up this column. The column is about 2 or 3 meters tall. And then we have cameras, detectors, spectrometers, which are located either at the bottom of the column or at various other points. They could be some way halfway up the column as well. So this is what a modern electron microscope looks like. And as I mentioned, we are looking at relativistic electrons, but we are also looking at matter on the atomic scale. So in some ways, you could think of it as a physics experiment which mixes special relativity and quantum physics. There's another interesting aspect about electron microscopes, which is that typically a sample which we examine has to be between a few atoms thick and a few hundred atoms thick to be transparent to electrons which pass through it. But if you calculate how many electrons are typically in the column at any one time, then with most imaging modes, electrons are on average about 10 microns apart as they travel down the column at above half the speed of light. This means they're spaced by much more than the thickness of the material that we ever examine, and yet we observe diffraction and interference phenomena, while at the same time, when electrons interact with the detector at the bottom of the microscope, they interact individually as particles. So every time we perform an interference experiment with an electron microscope, we see wave-particle duality in front of us. The electrons behave as waves, they're detected as particles. And I'll probably come to that in more detail in the second lecture tomorrow. So this is what a modern microscope looks like. I'll come back to what is going on inside the microscope in a few slides. But just to provide a short historical note, the electron microscope was invented in the 1920s and 30s, in particular by Max Knoll and Ernst Ruska. They made use of a discovery that had been made some years earlier, that coils that carry current can focus electron beams. And the invention of the microscope came not long after the wave nature of the electron was first demonstrated in the 1920s, and not so long after the particle nature of the electron was first described in the late 1890s. So to begin with, I'd like to start off with an image of what we typically see in the electron microscope, and I'd like to use this as motivation for how we try to understand the images that we record. So this is a typical atomic resolution electron micrograph. And what we see on here is an image of a small metallic particle. This is a particle of platinum, which is used in a catalyst. In fact, I think it's a catalyst used in a car exhaust. This is a three-dimensional particle. It's roughly octahedral in shape. But when we record an image in the electron microscope at atomic resolution, what we see is a set of small white features which appear to be individual atomic columns. We don't see much information about the three-dimensional shape of the particle, and we don't see much information about the chemistry, what each atomic column is, whether it's, in this case, platinum, or whether it's something else, carbon, oxygen, or something else. So one question I would like to answer during the talk is, what exactly are we looking at when we record an atomic resolution electron micrograph like this? Do the white features really represent atomic columns? If not, what do they show? And how have images like this evolved over recent generations of microscopes over the last 10 or 20 years, and how could they improve in the future? But back first of all to the motivation for why we record images in electron microscopes at all. And I start here with an image of what would be a state-of-the-art microscope some 20 years ago. And again, just as in the image which I showed before, what we have is a vertical column with an electron gun at the top, a sample halfway down, detectors at the bottom, and on this type of instrument you would have a console with someone sitting in front of it. So the main reason instruments like this are very versatile and useful, and why they provide information which goes beyond what you can record with, let's say, X-rays, neutrons, or surface-sensitive techniques, is that you can get local information about a huge variety of different material properties. And this is about both biological samples and about physical sciences, inorganic samples. But today I'll concentrate mainly on inorganic materials. So this information can record information about crystallography, about strain. It can record information about local chemistry, spectroscopy, valence states, and also about functional properties of materials. All of this can be done while looking at operating, working devices or experiments. You can put gases into the microscope column and look at chemical reactions happening in real time on the atomic scale. And you can also introduce stimuli. You can introduce light, you can introduce mechanical stimuli, or, for example, applied voltages, applied fields on the nanoscale to look at how materials respond to external stimuli, but on the local scale. So, in the electron microscope, there are a number of different signals which you can record. What happens is that a high-energy electron comes down and interacts with a thin sample. And as I mentioned, thin means between a few atoms and a few hundred atoms thick. And in practice, the sample responds in many different ways. You can have visible light, cathodoluminescence. You can have secondary electrons emitted, characteristic X-rays, which I'll come back to if there's time. Phonons, in other words, vibrational modes of the sample, heat. But in practice, for obtaining practical information about materials, we're mostly interested in electrons which are almost undeflected. In other words, small angle scattering. Electrons which pass down the column, and then we can use angle limiting apertures to define which electrons contribute to the image formation process. And those electrons can either be recorded as images or as diffraction patterns, or they can be passed through to a spectrometer. And so these are the different signals which we typically record: images, diffraction patterns, or spectra. And today I'll primarily concentrate on imaging, image formation, and I'll try to describe exactly what the images tell us about materials. One point I should mention is that there are a multitude of different ways of operating electron microscopes. The two broadest categories are what are referred to as conventional high-resolution imaging and scanning transmission electron microscopy. In conventional high-resolution imaging, what you do is you let a broad beam of electrons, effectively a plane electron wave, come down and interact with the sample, pass through the sample, and then a high-quality imaging lens, an objective lens, is used to focus an image of the sample onto a detector, and then some way between the lens and the detector you have diffraction planes where diffraction patterns are physically present inside the microscope column. There's a second imaging mode, which is scanning transmission electron microscopy. And in this case, a lens is used to focus electrons onto a sample, and that focused electron beam can have atomic dimensions, and then that focused beam is rastered or scanned across the sample, and then diffraction patterns typically are collected point by point as the beam is moved from atomic column to atomic column. I'll mainly concentrate on the images on the left. This is also referred to as coherent imaging, and this is because effectively what we form are interference patterns in the electron microscope. These are not just projections of the sample, and I'll explain why they're not so easy to interpret and how we do interpret them in practice. So if we look inside an electron microscope column, what we don't see is glass lenses as you would have for light. You have electromagnetic lenses. We don't see much empty space. The electron microscope is full of metallic windings. Each of these windings constitutes one lens. The sample sits roughly halfway up. It's normally very small, only a few millimeters across. And as I mentioned, it can be only a few atoms thick. And then the lenses above the sample are used to focus either a broad beam of electrons or a focused beam of electrons onto the sample. And below you have magnifying lenses. And then all sorts of other components, apertures, spectrometers, and so on. The electron beam is this very narrow red line which passes up down the middle of the column, and it's only a fraction of a millimeter wide typically, and I'll explain in a few moments why it's only a fraction of a millimeter wide. So if you took a photograph, if you cut a column in half, and sometimes people have done this when instead of throwing away a microscope, then you can see the path of the electron beam, the emitter where the electrons are first generated and accelerated, and then you have the windings, the coils. The sample sits at this level, and then the magnifying lens is down here. Now, in the electron microscope, typically we describe image formation in terms of Abbe's theory of image formation. It's an approximation which happens to be valid for high-energy electrons in the transmission electron microscope. And according to this approximation, if we have a plane electron wave passing through a thin specimen, and we have one imaging lens which focuses an image of the sample onto a detector, then in between the lens and the detector we have what's termed a backfocal plane, and in the backfocal plane you focus a diffraction pattern, the diffraction pattern that would normally be formed at infinity. It's focused at the focal plane of the objective lens, and in the backfocal plane electrons which have been diffracted in a particular direction are focused onto the same position in the backfocal plane. In other words, this is a diffraction pattern, a map of angular scattering. The way the electron microscope operates is that as you go from the sample to the detector plane, you have multiple image planes and multiple diffraction planes. And as you switch from recording an image to a diffraction pattern, you just change the strengths of the lower lenses so they focus onto either an image or a diffraction plane which is formed higher up in the microscope column. So I mentioned that we're dealing with very small scattering angles, And I mentioned the word resolution as well. And I'd like to go a little bit deeper into what we mean by resolution in electron microscopy. But first of all, scattering angles. Why is the electron beam coming down the column in such a very narrow pencil-like beam? There are two primary reasons. One reason comes from considering the Bragg equation, which is applicable to many different types of scattering phenomena. So the Bragg equation describes the scattering angles at which you have coherent superposition of scattered intensity from different atomic planes. In the electron microscope, the typical wavelength of the high-energy electrons is a few picometers. The typical interatomic spacing is between 1 and 2 angstroms. And as a result, the typical scattering angles are on the order of a fraction of a degree or perhaps less than a few degrees. So inherently, most electrons are only scattered to very small angles as they pass through materials. The second reason that the electrons pass down a very narrow beam down the microscope column is related to aberrations of the electron microscope lenses. If you calculated what the resolution of an imaging system would be for an electron microscope using a normal criterion such as a Rayleigh resolution criterion, in other words, where a spot on the sample is imaged onto an airy disk in the detection plane. And if you, again, put the typical electron wavelength into the equation for the Rayleigh resolution, and if you assumed that you could form an image using electrons that had been scattered out to a larger angle, for example, somewhere around 100 milliradians, then you would predict that the resolution of the imaging system in a microscope would allow you to record images with a spatial resolution which was somewhere around 0.1 of an angstrom, about 10 to 20 times smaller than an intraatomic spacing. In practice, the resolution of electron microscopes is nowhere near this value. It's normally about 100 times the electron wavelength, and this is because of aberrations of the electron microscope lenses, and that's something I'll come to. There is another complication in electron microscopy, and this is related to the fact that electrons scatter extremely strongly in materials, much more strongly than X-rays or neutrons. This is one reason why electron microscope samples have to be just a few atoms or a few tens to hundreds of atoms thick. But the result is also that the images that are recorded tend to be very complicated because of multiple scattering. For heavy atoms, even 1 to 2 atomic layers of material already result in multiple scattering of relativistic electrons as they pass through a sample. So what I'm showing here is an image of a semiconductor device, an atomic resolution image, which shows a crystalline region on the left, polycrystalline regions on the right, and an amorphous region in between. The scale bar is 5 nanometers. As a result of all of these complications, these white features here, which look like atomic scale features, are not necessarily representative of where the atomic columns really are. You have all sorts of multiple scattering diffraction phenomena, and the image approximately tells you which regions of the image are crystalline, which are amorphous, and which are polycrystalline, but it's extremely difficult to interpret. In other words, you have multiple scattering, and when you have images which are formed, images which look like atomic resolution images, they are not just projections of the crystal structure. In fact, what happens is they are interference phenomena where you interfere electrons which have been unscattered with electrons which have been scattered to different angles. And the images are complicated because those interference patterns are sensitive to how you align your electron microscope, even what defocus you set your imaging lens to. And they're also sensitive to how thick your sample is and exactly what the orientation of your sample is relative to your incident electron beam. This is one reason why it's very difficult to describe phenomena in electron microscopy analytically, because right from 1 or 2 atomic layers thick, you already have a complicated multiple scattering process which is usually only described numerically through simulations. Now, I mentioned aberrations as one reason why resolution of electron microscopes is limited, and also why you don't normally use electrons which travel far from the optic axis of the microscope. The main resolution limiting aberration in electron microscopy is spherical aberration. And the lowest order of spherical aberration describes how electrons which travel at different distances from the optic axis have different focal lengths. So a point on an object in a sample is no longer imaged as a point on the detector, but as a blurred region. You can compensate for this aberration to a small extent by placing the detector not at this position, but over here. And this is known as the disk of least confusion in electron microscopy. But you still image a point as a blurred region and not as a point. And this brings me to resolution in electron microscopy and how aberrations are described when you think of spatial resolution. Now, resolution has many different definitions in different subjects. For example, you can have diffraction limited resolution, where you place an angle limiting aperture in the optical system, and then the resolution typically scales as 1 over the size of the aperture. With aberrations, it's a little bit more complicated, and in electron microscopy, you normally describe resolution in terms of what is referred to as an aberration function, and specifically, you plot the sign of an aberration function. Now, in electron microscopy, you have many orders of aberrations, but the 2 most significant ones are the defocus of the imaging lens, that's also referred to as an aberration, and the first order spherical aberration. The aberration function is described by the equation which is shown on the top right. And in this equation, lambda is the wavelength of the high energy electrons, a few picometers. F is the defocus of the objective lens, which is used to form the image. And CS is known as the coefficient of spherical aberration. Typically, it has a value of a few millimeters for a normal imaging lens. If you plot the sign of the aberration function, it will vary as you change the defocus of your objective lens. This is a parameter you normally have control over. The spherical aberration coefficient of the objective lens is a parameter which you normally have no control over. And so when you try to optimize spatial resolution, you usually change the defocus of the objective lens to try to offset the unavoidable spherical aberration of the imaging system. I'll explain in a moment why the sign of the aberration function is important and not the aberration function itself. But under optimal imaging conditions, when you balance the defocus and the spherical aberration optimally, the sign of the aberration function has a broad plateau and then it oscillates many times. What the sign of the aberration function tells you in practice is the way in which different spatial frequencies in the object are transferred to the image. And this sign of the aberration function is plotted as a function of spatial frequency. In other words, now we are in Fourier or reciprocal space. We have low spatial frequencies on the right, high spatial frequencies in the image, low spatial frequencies on the left, high spatial frequencies on the right. And what this broad plateau tells you is that low to medium spatial frequencies in the image are transferred with dark contrast, and then beyond a certain spatial frequency, the spatial frequencies in the object are transferred either as black or as white contrast. In other words, the information is effectively scrambled. This point here, this crossing, is referred to as the point resolution of the microscope, of the imaging system, under optimal imaging conditions. And that is approximately the best spatial resolution that you can obtain in the presence of spherical aberration. And this is referred to as the Scherzer focus condition. Now, this sign of the aberration function affects images for a very specific reason, which I'll try to go through now. And here I have a few equations on this slide and on the next one. So normally, we consider the electrons which come down the microscope column and through the sample as a complex wave which has a certain amplitude and a certain phase. And then the image intensity is the complex wave function times its complex conjugate when it's recorded on the detector plane. The effect of aberrations, including defocus of the imaging lens, is to introduce a type of blurring or point spread function. And that point spread function can be described by a convolution in real space, in the image, or equivalently, in the diffraction plane, in Fourier space, in reciprocal space, it can be described as a multiplication by the Fourier transform of this blurring function. Now, this blurring function in reciprocal space has a number of different contributions. The effect of an aperture, some envelope functions which describe partial coherence, partial spatial and partial temporal coherence, which I won't go into now. And then e to the I times the aberration function, which I introduced on the previous slide. And the aberration function is again shown here, but now with the reciprocal space coordinates in 2 dimensions. How does this affect the image intensity? Well, for a very thin sample, which can be regarded as a phase object that changes the amplitude and the phase of the electron wave, it changes the phase of the electron wave approximately proportional to the electrostatic potential of the atoms inside the sample. So there's an interaction constant times a projected potential inside e to the minus I times a phase shift. If you have a very thin sample, then this term inside the exponential is small, and you can expand the exponential to its first term. And then you can combine this expression for the electron wave function in real space with the expressions for the blurring or point spread function that includes the aberration term. Either in real space through a convolution, or in Fourier space through a multiplication by the Fourier transform of the real space blurring function. And if you then expand the exponential e to the I chi as a cos plus I sine, and then convert back into real space and evaluate the image intensity as the electron wave function times its complex conjugate, you get an expression for the image intensity, which is approximately, for a thin specimen, 1 plus 2 times a constant times the projected specimen potential times the Fourier transform of sine times the aberration function. And this is why sine times the aberration function is, in practice, the quantity which describes the blurring in experimental high-resolution images. This is all an approximation for a very thin sample and for a sample which has a practical thickness, even just above a few atomic layers. This calculation is no longer valid, and you have to do a numerical propagation of the complex electron wave function through the quantum mechanical specimen potential using simulations. But this explains why the sign of the aberration function is in practice the blurring function. There is another feature of image formation in high-resolution electron microscopy, which is often observed experimentally. And this is the fact that as you change the defocus of the imaging or objective lens, you come back to the same type of image again and again and again. And halfway between those defocus values, you come back to approximately the inverse of the image you started with. If you look up in Wikipedia an effect called the Tolbert effect, this is exactly what is happening in electron microscopy. These are referred to as Tolbert images or self-images or Fourier images. And they describe the fact that under a near-field approximation, as you change the defocus of the imaging lens, then the image repeats in even steps of defocus, and those steps in defocus are given by twice d squared over lambda. Lambda is the wavelength, in this case of electrons, and d is the dominant periodicity in the image, which repeats. And again, just as before, it's possible to derive this formula. It's easiest to derive it for a single spatial frequency. And in this case, it's possible to write the wave function of an electron as a single, in terms of a single spatial frequency, like a single sine wave. And then in Fourier space, in reciprocal space, that corresponds to a single delta function, a single peak in Fourier space. There are 3 or 4 different approaches for deriving this formula, but in this case, if we go back to the aberration function and just include the defocus term, and then if we apply the defocus term inside the e to the I chi, e to the I times the aberration function, but just including the defocus term in the aberration function, but just for a single periodicity in Fourier space, and then we evaluate this expression back in real space, we end up with a function which repeats in defocus such that the term inside the exponent here repeats in defocus whenever the 2 defocus values satisfy this expression here. The difference between these 2 terms for different defocus values is 2 pi times an integer. In other words, when the change in defocus is 2d squared over lambda times an integer, exactly the expression on the previous slide. Now, that was what happens if you have an electron microscope with aberrations in the objective lens. And I started off by showing an image of an electron microscope that would have been state-of-the-art 20 years ago. But 20 years ago, there was a revolution in electron microscopy, and that was the development of hardware aberration correction. And this ability to correct for aberrations of electron microscope lenses dates back to a discussion from the 1930s, two papers by someone called Otto Scherzer, who stated that for a round, rotationally symmetrical electromagnetic lens, or magnetic lens, spherical aberration is unavoidable, and the only way to overcome spherical aberration is either to depart from rotational symmetry of the magnetic lenses, or to make the magnetic field of the lens time varying, or to introduce electrostatic charges along the optic axis of the microscope. And the first of these approaches, which was realized in practice, was to depart from rotational symmetry of lenses, and that was done in the early to mid 1990s. Here's an example of a magnetic multipole. You now have poles of many different orders, quadrupoles, sextupoles, hexapoles, octupoles, which can be assembled in a sequence. They don't replace the normal imaging lens, the normal objective lens of a microscope, which is still rotationally symmetrical, but they can be assembled alongside an objective lens to correct for the dominant or spherical aberration. This was the first microscope which incorporated one of these aberration correctors in the institute where I now work in Jülich. It's an extra component of the column, which in this case is 30 or 40 centimeters tall. And this resulted in a revolution in resolution in electron microscopy. And it improved the resolution by more than a factor of 2 from what you could achieve with conventional non-aberration corrected instruments. And what does this do to the transfer function? Well, it makes the transfer function much simpler. Not only that, but now you can tune not only the defocus of the lens, but you can also tune the spherical aberration coefficient to any value you want. And for a number of reasons, it turns out that you don't actually want to set the spherical aberration coefficient to exactly 0, but you want to set it usually to a slightly negative value and then image with a slightly positive value of objective lens defocus. The transfer function then starts to look much simpler. It extends much further to higher spatial frequencies. In other words, the resolution of the imaging system is improved. There is still a decrease at higher spatial frequencies. This is for a different reason. This is because of partial spatial coherence, because of the finite size of the electron source and the finite energy spread of the electron source. And you're still missing low spatial frequencies. That's for a different reason. If you think back to the original image I showed of this small platinum particle, which was just a few nanometers across, that image looked very flat. The particle was three-dimensional, but you couldn't tell there was a three-dimensional variation in intensity. This is because whether you correct for aberrations or not, the low spatial frequencies are still missing, and that's described nicely by the aberration function. But now, the spatial frequencies which are accessible extend out to higher spatial frequencies, lower periodicities in real space. The image is much more directly interpretable up to what is referred to as the information limit of the microscope, which describes the partial spatial coherence. And under optimal imaging conditions, atomic columns appear white. They don't appear dark or vary from dark to bright, depending on spatial frequency. what is the result? The result is you have beautiful electron microscope images. This is an image obtained by my colleague Chunlin Jia in Jülich of an oxide. This is barium titanate, and in most materials in electron microscopy you look not at perfect regions of material but at defects to try to understand why materials have certain mechanical or electrical or magnetic properties. And in this case it's twin boundaries that are of interest, and under these imaging conditions, these very specific imaging conditions, this image can now be interpreted faithfully. You can interpret not only the positions but also the heights of the individual white features corresponding to where the atomic columns are, and this is both the light atomic columns, in this case oxygen, and the heavier atomic columns, barium and titanium. None of this would be possible without aberration correction. This is all still done in transmission. The high energy electrons are still passing through the sample, and now the spatial resolution is not 100 times the electron wavelength, it's about 40 times the electron wavelength. It's still not diffraction limited, but it's improved very significantly. I mentioned that the defocus and the first order spherical aberration coefficient are just the first two aberration coefficients that need to be considered. There are many, many others. They go up to now seventh order, which can be corrected in practice. And some of the aberration correctors now have 200 or 300 power supplies controlling all the different magnetic elements inside them. And some of the power supplies need, in some cases, some of the most sensitive power supplies which are used for any scientific application of any kind. And nowadays we are even approaching the physical limit of what is possible with these types of aberration correctors. It's really limited by fundamental physics, in some cases by the uncertainty principle, what resolution can be obtained. A graph which is sometimes shown is the evolution of resolution of imaging systems over time. The vertical axis is on a log scale here. The horizontal axis is in years. We have light microscopy, then we have electron microscopy in the present without aberration correction, and then we have electron microscopy with aberration correction. In each case there's a kind of plateau before each successive resolution occurs, but nowadays the spatial resolution is about half an angstrom, in other words about 3 times smaller than a typical intraatomic spacing. Are the images easy to interpret? Well, yes and no. Under certain circumstances you can. What I'm showing on this slide is experimental images which are recorded from another oxide, strontium titanate. Now with aberration correction, but the different rows correspond to different settings of the objective lens. And for this particular sample thickness, the contrast still varies quite rapidly with sample thickness and with objective lens focus, even in the presence of spherical aberration correction. And in practice, even with aberration correction, often quantitative comparisons are needed with simulations of the images, and the simulations often require models for the electrostatic potential in the sample, which take into account bonding effects, often quantum mechanical effects. And this is where quantum mechanics meets special relativity in electron microscopy. Another point which I wanted to make is that for a thin sample, you have what is almost a phase object, even though as your electron beam, an electron wave passes through a thin sample, then its amplitude is changed and its phase is changed. For a very thin material, it's primarily the phase which is changed. And the phase is changed by the local electrostatic potential of the atoms. But if you had a perfect imaging system, if you had a perfect lens and you reformed an image on the detector plane which was perfectly in focus, then you would see no contrast at all when you recorded the complex wave function times its complex conjugate for pure phase object. And this is why one reason why in practice we still want aberrations, we still want some defocus and some other aberrations to introduce contrast, either through aberrations or through parameters we control like defocus or through apertures. Otherwise, for thin objects, we would see nothing at all. I just want to check on the time. So perhaps in the last 10 minutes or so, I wanted to go through another reason why images and not diffraction patterns, but what I call diffractograms are useful in electron microscopy. And these are some slides which are taken from some exercises which we run in Arizona State University. But I wanted to go through some of the slides without running through the exercise itself, because they still serve a useful purpose. So first of all, what is a diffractogram rather than a diffraction pattern? Well, on the left of this slide here, what I'm showing is an image recorded in a non-aberration corrected electron microscope of an amorphous thin film with some small particles of gold on it. So each of these particles, which look dark here, is perhaps 2 or 3 nanometers in size. You might occasionally be able to see some atomic planes. And then in between you have what looks like an amorphous region, and this is an amorphous carbon support film which underlies the small metallic particles. If you were to record a diffraction pattern by pressing the diffraction button on an electron microscope, what you would see is some diffraction spots corresponding to the angles at which you have lattice planes which are diffracting in particular directions according to the Bragg's law. And you might see some other background contrast from scattering from the amorphous material. A diffractogram, in contrast to a diffraction pattern, is obtained by taking an image, recording the intensity, and then calculating its Fourier transform times the complex conjugate of the Fourier transform. In other words, the modulus or the modulus squared of the Fourier transform of an image. And again, it's an image or diffractogram which tells you something about Fourier space, about reciprocal space, but it gives you different information from what you would record in a real diffraction pattern. The difference is that what you see in a diffractogram is exactly what you would have in a diffraction pattern. In this case, you can see spots here corresponding to diffraction from certain planes in the gold crystals. But in addition, you've got a set of rings here. And the rings are in fact going out from the origin the sine squared of the aberration function which I described earlier. And why is that useful? Well, these rings are independent of what sample you put in the microscope column, but they are sensitive to the imaging conditions and some fundamental parameters like the aberration coefficients. And so what the aim of this exercise was to try to understand how to interpret the positions of these rings to tell you under what conditions the microscope was being operated at the time, specifically to work out what the defocus of the imaging lens was and what the spherical aberration coefficient of the microscope was. And this is not possible from a diffraction pattern. It is possible from the Fourier transform of an image. They're different things. So in the diffractogram, what you have is you have these envelope functions which I described before, but now you have the modulus squared of each of these functions, including the sine of the aberration function, times the specimen potential squared. And in this case, you have some background intensity because you have an amorphous region. This is the Fourier transform of the specimen potential corresponding to the amorphous support film underlying the gold crystals. And what do you see in the diffractogram? Well, that is related precisely to the aberration function and to the sine squared of the aberration function. Now, I mentioned before that in the aberration function, the two lowest order terms correspond to the defocus and the spherical aberration. One of them is quadratic in spatial frequency, and one of them goes as the spatial frequency to the power fourth. You can use the defocus to offset, which goes as the square of the spatial frequency, to offset the term in the spherical aberration, which goes as the spatial frequency to the power fourth, in such a way that the aberration function chi takes different forms as you change the defocus of the objective lens. There's an optimal focus, which is Scherzer focus, which I mentioned earlier, and that corresponds to the green curve here. That's when sine of chi is very close to minus pi by 2 for the largest range of spatial frequencies possible. And then there is something which is called extended Scherzer. There is something called Gaussian focus, which corresponds to the defocus being set to 0 and just the spherical aberration term. And then there is another defocus called minimum contrast focus, and they all have different, they can all be described using different expressions. There are envelope functions as well, and this is why the contrast dies off at high spatial frequencies. There are two envelope functions. One corresponds to the finite size of the electron source. There's an expression here which depends on objective lens defocus, which I won't go through in detail. And there is the temporal coherence, which corresponds to the finite energy spread of the electron source. And there's a separate term here which does not depend on defocus. And there is a defocus dependence because of the combined envelope function. One is multiplied by the other, and the defocus dependence comes from the term which describes the finite size of the electron source. If you multiply the envelope functions by the sine of the aberration function, in this case it's the sine and not the sine squared, then you end up with these 5 different green curves for the 5 different defocus values which I showed on the previous slide. And these 5 different green curves describe exactly what you would see if you recorded images at these defocus values, and they also describe exactly where these dark rings occur when you take a Fourier transform of the images which you record. So the dark rings would be at the spatial frequencies at which the sine of the aberration function goes through 0. This curve down here corresponds to Scherzer defocus. In other words, the defocus which I showed way back in the previous slide, the optimal defocus for imaging in the presence of spherical aberration. There's a reason why we sometimes go to much higher underfocus values, and this is because you get extended pass bands at higher spatial frequencies, but some of the lower spatial frequencies are scrambled, and the images at the top correspond to 0 defocus and minimum contrast focus. And why are these useful? Well, they're useful because if you measure the spatial frequencies at which each of these black rings occurs, it turns out that these minima occur when the aberration function at values where chi takes values of n times pi by 2. What this means is that when you set the expression for chi equal to n times pi by 2, you end up with an expression which defines the defocus and the spherical aberration at which each of these black rings occurs. And one way in which you can manually work out what the defocus and the spherical aberration coefficient is simply to measure these spatial frequencies and then to plot on the vertical axis n over u squared, where u is each of these spatial frequencies, and on the horizontal axis u squared. Then you end up with a straight line where the intercept with the vertical axis gives you 2 times the wavelength times the defocus, and the slope is given by the wavelength cubed times the spherical aberration coefficient. And this explains why taking Fourier transforms of high-resolution TEM images is useful for determining the imaging properties of the microscope, independent of what sample you have in the microscope. And this is in practice how microscopes are aligned automatically nowadays. You record images as a function of not just defocus, but also as a function of incident beam tilt. And you can now automate the analysis of digital diffractograms like this. When we run this exercise in practice, and when people measure the positions of these rings, it turns out that, especially for the measurement of the spherical aberration coefficient, everyone gets a wildly different answer. And the reason is because even if you measure these positions as accurately as you can, it's extremely difficult to measure some of the aberration coefficients. You get very large error bars which not only depend on how these positions are measured, but also on whether they are on a sloping background. And this also explains why automated routines are now required for measuring aberration coefficients in practice. If you want to try to understand aberration functions and the sign of the aberration function in practice, there is some software which is available free online. It's called CTF Explorer. And in this software, you can key in the parameters which describe any electron microscope, and you will immediately and visually be able to see how the transfer function varies as a function of many aberration coefficients. And this is a useful tool to try to understand imaging processes in the electron microscope. And that's more or less what I wanted to say today. And maybe I'll just conclude by explaining why I structured the talk like this. So, first of all, I wanted to explain why spatial resolution is a relatively complicated concept in electron microscopy, how it depends on parameters which you can control and which you cannot control, and also how efforts have been made to try to improve spatial resolution over time, and then the present status of where we are with spherical aberration correction, which is a spatial resolution of about 40 times the electron wavelength, but also the fact that even though we understand the imaging process and the scattering processes in materials very well physically, interpreting experimental images is still not straightforward. What we record are not direct projections, they are interference phenomena which depend on a huge number of parameters. And when we do calculations, normally you have 30 or 40 parameters that have to be included which describe the sample the electron microscope column, the imaging conditions, and those parameters often need to be varied iteratively until you obtain a best match with simulations to understand experimental observations. And again, I don't know whether this is a good or bad thing, but there weren't so many equations here. It's possible to describe electron optics and also the way in which magnetic or electrostatic lenses work very theoretically, but I wanted to concentrate on concepts of where we are in electron microscopy and what is possible. So the talk was necessarily a little bit more applied and, as I mentioned, more about concepts. I was told I should stop now, and then we'll carry on with something more specialized tomorrow. So.
We have time for a few questions. Okay. Let me activate the microphone. Yes. Okay. Who's first? Okay. Let's start here.
I want to ask you about scanning tunneling microscope (STM) phenomena.
Scanning tunneling microscopy?
Yeah.
You mean with a scanning probe?
How she happened from the photo of electron microscope?
So everything we've been discussing today is not with a scanning probe. It's all about passing a high-energy electron beam through a thin sample. So it's nothing to do with a scanning probe. Scanning probe microscopy is more of a surface technique, and in this case, we're just dealing with free space electrons which pass through, high-energy electrons which pass through materials. With scanning tunneling microscopy, scanning probe microscopy, this is a completely different discipline, and nowadays it's there are some efforts at applying transmission electron microscopy and scanning probe microscopy to the same region of the same sample to obtain different information, but they are very separate subjects at the moment.
Okay. Actually, I have 3 questions. Okay. The first one is about the electron velocity is about half the speed of light, right? Does this velocity affect the structure of the molecular material sample?
That's a good question. Maybe I answered that one before you asked the next two, so I remember. So the fact that we are dealing with relativistic electrons has many consequences. The first consequence is the way in which we describe the interaction of the electron beam with the sample, because the high-energy electrons interact very little with the conduction electrons inside the sample, at least when we think about elastic scattering. And this means that the entire scattering process can be described by a Schrödinger equation where the only thing we need to do is change the mass of the incoming electrons to be a relativistic mass. And it's much simpler than dealing with lower energy electrons which interact with matter. But your question was whether high energy electrons change the structure of the sample, and the answer is yes, both for biological samples and for inorganic samples. And they change the structure in many different ways. One way is simply by physical knock-on damage, momentum transfer to the atoms inside the sample. You can have atoms which are displaced or sputtered off the sample by the incident electron beam. But they can also ionize the sample, create effectively radiation damage inside the sample, and depending on what materials you're looking at, you have different types of damage process. For biological samples, it is one of the main limiting factors, And normally, for imaging individual proteins, you have a maximum electron dose before the sample is destroyed of typically less than a few tens of electrons per square angstrom. In our material science applications, we sometimes use tens of thousands of electrons per square angstrom to form our images. But if you record successive images, almost every image looks slightly different, and you have to be extremely careful with what the electron beam is doing to the sample. Tomorrow, I'll probably begin by explaining how we're trying to overcome damage processes while retaining spatial resolution.
Okay. My question is, where we put the sample to examine it, or
Where do you get the sample to examine it? Do you mean how do you make a very thin sample?
No, where we put the sample and scatter the electrons on it.
Sorry, I don't understand.
He asked that the sample, when you put on the slice, maybe the scattering show the table atoms, or
It should move the atoms or tilt them. You mean momentum transfer to the sample from the incident electron beam?
I mean that the electrons does not distinguish between the sample and the slice which the sample put in.
Okay. So you have a sample on a substrate.
Yeah.
Everything we do is in transmission. So very often, if you have a support film, a substrate, it is as thin as possible. Often it's something which is very light, low atomic number, and very thin, sometimes only a few nanometers thick. But normally, if it is made of an amorphous material, even if it's thicker, then it just contributes a background underneath the intensity of the crystalline sample that you're most interested in. But normally, you have to minimize the thickness of the underlying support film, and making a sample which is only a few nanometers thick is one of the biggest challenges, especially from a site-specific region of a material, if you don't want to damage the sample you want to look at while you're making it very thin. So sample preparation for electron microscopy is an art in itself, and there are many different techniques, ranging from chemical approaches to bombarding with ions, to physical cutting with diamond knives, which are all used to make electron transparent samples.
So how we can know this is the atoms of the sample and this is the atoms of background?
Normally, you choose the support film so that you can easily distinguish what is the sample and what is the support film. For example, an amorphous material has very different contrast from a crystalline material. And sometimes you can do chemically sensitive imaging, which I didn't mention today, spectroscopic imaging column by column, and then you can distinguish chemically between what you're looking at and an underlying film. But this is a different technique which I didn't describe today. You can now do chemical analysis atomic column by atomic column using a different approach.
Thank you.
Can you measure samples in vacuum? You mean floating with no support? I think that's never been done before. People have tried to do it, for example, by firing droplets of containing atoms, containing molecules through the path of the electron beam. But so far this hasn't been very successful. And one reason, I think, is because most samples charge up when they when high energy electrons hit them because of the emission of secondary electrons, and unless they're on a support film, there's no way for the charging to be compensated. So in practice, I think people have mentioned it many times, but imaging samples without a support at all is beyond what's been done so far. I guess you could make some kind of Paul trap in the electron microscope, but it's not.
We have one question from Beata, I suppose. So maybe wait 1 second. Hello. Hi. Okay. So we're here, and maybe you could tell me your question, and I'll repeat it again.
Yeah. The student will ask you now.
Okay. Excellent. Hello. Very good. How are you? Okay. So you're live. So let's hear your question.
Nowadays we use artificial intelligence and deep learning. What is that used in electron microscopy, and what is the advantage of use this technique or this?
Okay, so if
Not related question, but it is trend in this age.
if I understood the question, it's whether artificial intelligence and deep learning can be used in electron microscopy. Is that correct?
Again, please.
So the question was, can artificial intelligence and deep learning be used in electron microscopy? Yes? Okay. The answer is in principle yes, and nowadays it's just starting to be applied. You can now, people are just starting to train algorithms to interpret experimental images by simulating images for many different three-dimensional configurations of atoms, and then training algorithms to be able to interpret images based on large collections of simulations. But this is something which is just starting within the last few months. So I think it's a very good direction. It's a very powerful direction to go in, to use some kind of forward models together with deep learning approaches.
Okay. Okay. So, okay, thank you. Okay, so I think we're about out of time. So let's all thank Professor Rafal one more time. And we'll start again in about 15 minutes. So a brief break now.
yes, it's perfect. It's not an easy one.
Okay, everyone, welcome back for the last lecture of today. We are extremely happy to have Professor Beata Kardynal, also from Jülich, telling us about semiconductor quantum optics.
Good afternoon, everyone. Well, I think first of all, I have to warn you, I speak a lot, and I don't think I will say as much as I want. Your task is to stop me if I'm too fast, and please ask questions as I go. And because I talk a lot, we'll see how far I can go with the semiconductor. So my plan for the lectures is here. I would like to start from, well, actually, I would start from point 2. So I'll compare the classical and quantum state of light, and then go into why semiconductors. And you know, usually you start bothering with materials like that when you have some applications in mind. And I will keep 2 applications in mind. One would be the quantum key distribution, and then use of photon-photon entanglement. Then, if I don't talk too much, we will go into talking about 2-level systems in semiconductors, so realization of sources of these strange quantum states of light, and how they interact with light. So as I say, please stop me at any time and ask questions as we go. Right, so I think we are all familiar with classical Maxwell equations. And this set that I gave you here, of course, describes electromagnetic wave in vacuum. We see it from the lack of charges and currents. And they can be folded into one very neat equation, given here, where change of electric field in space is related to its change in time. This is, again, equation in vacuum. This is why we have the speed of light in vacuum. If we go into materials, we have to change the speed into the speed in a material. And here you have to be incredibly careful, because this only works if there is no absorption. So this is something to remember. Once we have absorption, the equations are much harder to solve. The solutions are actually, you have a huge choice of solutions. Anything that relates space and time with this argument would work. And when you go into quantum optics, it's very convenient to use this particular form of solution. It's a little bit different to what you might be used to, which is given here. But if you do a little bit of algebra, you will find that the 2 of them are compatible within the factor of 2 in amplitude. We have here 2 terms. One is E plus and E minus. And E plus behaves as we would expect in time. Time goes forward. And this is a part of equation. This is part of the electric field, which we will associate with absorption of light. The other one would imply that time flows backwards, and we relate it usually to light emission, but you shouldn't be afraid. This is only mathematical trick. These are complex numbers which we don't measure. What we actually measure is only the real part of it. So we are not violating any laws yet. And again, when it comes to go into quantum description of light, it's very convenient to fold these equations. All equations are actually perhaps this one, and use a so-called vector field. A vector field can be related to electric and magnetic fields through very simple relationships. So you can see that electric field is just time derivative of this vector field. Therefore, again, think about it only in the terms of mathematics. And magnetic field is a cross product of nabla and vector field. And you will see later why I introduced it, but not that important. And of course, we all know how powerful Maxwell equations are. We can really describe pretty much everything we see. We can describe refraction, reflection, absorption, any macroscopic interaction of light with matter, and also pretty much interactions of electrons. However, we have a little bit of a problem when it comes to interactions on microscopic scale. That's where the classical description of light might not be that sufficient, and that's why we should really consider how to describe light in quantum terminology. And the first thing to do is rather simple, and it's to replace the electric field vectors, electric field expression with operators. And this is first quantization. So here you notice I will only work with the vector field, but as you remember, this is only a little bit of algebra that will take us back to electric or magnetic field, so nothing to be scared of. And now in the quantum picture, our operator of vector field is described through two operators, A and A dagger. Both of these operators are implicit functions of time, so please to remember it. Also when you read books, very often they come alone, just as I gave them, but they're implicit functions of time, and it's very, very important. Other than that, the spatial distribution remains as it is, and we have here what I didn't mention, of course, light carries electric field, and we have this little E vector that describes the polarization of light. And we will use polarization a lot, so therefore please remember that light can have two different polarizations, and each mode with different polarization, even if it is the same energy, the same wave vector, is a different mode of radiation. And again, as before, where the A plus and A minus parts of the fields were complex conjugates of each other, here in quantum language we'll call it Hermitian conjugate, but mathematical effect is the same. Now, so this is okay, but again, this form of quantized electric field is not very good when you want to see how photons, how light interacts with matter. For that, we need a second quantization. And second quantization is best described when you first think about harmonic oscillator. I think we all know pendulum, where energy moves between kinetic and potential energy. And it's described by this very simple Hamiltonian, where we have the elastic force, we have the potential energy and kinetic energy. The kinetic energy is a derivative d over dx, and these two quantities, momentum and positions, are canonical variables. And if you do a little bit of mathematics, you can actually create these two operators and a dagger, and no, this is not coincidence. You can express them in terms of these two canonical variables, and you end up with this rather neat looking Hamiltonian, which relates the energy of the system to the product of the two operators and with associated commutation relation. And this commutation relation is characteristic for bosons. Just a reminder that bosons have total angular momentum of h and multiples of those, unlike fermions, which scale in halves, and it makes a very big difference in when you calculate statistics. And what popped out here is the form of energy for electromagnetic fields. Again, you can see here that the energy associated with electric field and magnetic field oscillates in time in a very similar way to what you see in a harmonic oscillator. And without any proof, I can assure you that if you do a little bit of arithmetics, you will find that you can develop exactly the same Hamiltonian to describe light. So this is a second quantization for electromagnetic radiation. In this particular case, it represents one mode of radiation, and mode of radiation is always defined by omega, which is the frequency of radiation, and polarization vector. And the two operators, A and A dagger, are referred to as rising and lowering operator. And the name comes from the fact that if you act with a dagger on your quantum system of one mode of radiation, you are adding h omega of energy to this particular mode. If you repeat it many times, you add n times h omega. And that is already something slightly different to what you know from fermions. Of course, this h omega is an energy of a photon, and you can see that I can do it indefinitely. I can start from an empty mode, and I can add as many photons as I want. If they were fermions, we would be stuck at 1. And similarly, the lowering operator subtracts energy from the system. We are removing photons one by one from the system, and we cannot go anywhere below 0. When there are no photons in the system, there is still some energy, half of h omega, and this is the familiar vacuum energy. Vacuum state of radiation in quantum mechanics is just as important as 1 photon, 2 photons, 3 photons. Whenever you do any calculations, you have to include it. Otherwise, sooner or later, you will find yourself violating some laws of conservation. So as I say, the alternative name for the lowering and lowering and rising operator, here is a mistake, is annihilator or creation operator. And this is in reference to creating and removal of a photon from the system. So if you have many modes of radiation, then you have to sum over all of them, and your description of vector field of multi-mode radiation field then is this big sum. We are summing over wave vectors and polarizations. As once more, there are always 2 orthogonal polarization vectors. And we do the same with energy, with a full Hamiltonian. And now, if you look at how much energy there is in vacuum, you will find that it's actually quite a lot of energy, even if we don't have any photons. And here I'm repeating some of our commutation relations, and in particular, I would like you to have a look at this one. The lowering and rising operator don't commute only for the same mode of radiation. And I'm saying it because later on I would like to use these rules to show you how strange light is when we are actually working with quantum states of them. So here you are. So Fock state is actually the quantum radiation or non-classical radiation that I would like to spend some time on. And this state of radiation is by definition a eigenstate of a number operator. Number operator is defined here. This is just a product of a lowering and rising operator. And as you remember, order of operators matters. So it comes with this particular order, not other. And we first operate with the lowering operator and then with the rising operator. Now, this particular state of the eigenstate of this operator, as described here, has eigenvalue which is equal to the number of photons in particular mode. So it's very simple. But what could strike you here is that this is a precise number. There is no noise in it. This is a state which has n and only n photons. This is very different to what you would have in laser light, very different to what you have in light, daylight, chaotic light, as we see here. And this is first sign that this is slightly different to our classical light as we know it from daily experience. And here are some properties of this particular Fock states and that I would like us to use later in your problems. You will have the slides, so don't try to remember them. Try to understand them. So if we work with the rising operator on Fock state n, we will add a photon to the system, and there is some numerical prefactor that is associated with adding energy. Similarly, when you work with this lowering operator on Fock state n, you remove 1 photon, with some prefactor, again associated with removing energy from the system. And as we say, you cannot have less than 0 photons. So working with the lowering operator on vacuum state produces 0. Basically, this is not an action you can perform. And another very useful expression is given here. Here you see that an overlap between a Fock state with in mode L and mode L1 is only non-zero if this is the same mode. Or rather than, sorry, no, not mode. Yes, if you look at one particular mode, the states are orthogonal. The L's actually stand for Fock states, for number states. So, for example, 1 photon in a mode and 2 photons in a mode, they are orthogonal to each other, and therefore their overlap is 0. And now I have a little quiz for you. Who doesn't know what happens on a simple beam splitter with 50% transmission and 50% reflection when classical light falls on this beam splitter? Who does not know? I don't believe that. I know we all know. And the answer is it splits 50-50. 50% of light will be reflected, 50% of light will be transmitted. We can write it nicely formally. Probability of transmission is a half. What will happen if I have a number state, a Fock state, containing exactly 1 photon falling on the beam splitter? I can't hear you. Will it go through transmitted? Will it be reflected? I can't hear you. I think the first answer is correct. 50-50. There will be some times when the photon comes through, there will be some times when the photon is reflected. It behaves like a particle in this particular context, and this gives you an impression that quantum physics is very much about statistics. What we know in quantum physics is what we measure, and very rarely do we have a chance to measure just one instance. If we do, then there will be uncertainty. With 50% of time we will get this result, with 50% we will get that result. And formally, we can express it by calculating this probability, and just a refresher for those of you who had quantum mechanics and a definition for those of you who didn't. In order to calculate the probability of one particular outcome, in this case probability of photon being transmitted, I look at the entire wave function and multiply it by a complex conjugate of it. And by doing that, I'm also using the rule that I gave you before, that if I have 2 different modes of radiation, they don't commute. So this particular spatial overlap, again, for those who don't know, this scary-looking bracket notation is nothing else as a shorthand for an integral in space. So we are looking at how this particular probability is, or probability density of a photon in reflected mode, how it overlaps in space with the one that is transmitted in space. And this factor is therefore 0, and our probability of transmission is a half. Now a harder question. Here we have 2 photons, exactly 2 photons hitting a beam splitter. And my question to you is, we have 3 possible options, and we know that the sum, the square of these coefficients should add up to 1. Which of the 3 options will we observe on the output of the beam splitter? I guess we can use symmetry, and we can say that it could be either this pair, C1, C3, perhaps C2, perhaps all of them. What's your bet? Who goes for C1 and C3? Oh, don't be afraid to make a guess. Come on. Soon you will know the answer. Okay, so I can see that you are the only one who goes for this option. Who goes for C2? C2 looks most similar to classical, so who goes for C1? Okay, we have 2 people going for C2. The answer is all of them. And now you can see immediately that this Spock state is slightly different to what we expect, what we observe classically. We have this very strange situation where we have 2 photons coming on the beam splitter and they choose to leave together. That is not something we immediately think about. And this very fact, this very strange nature of bosons, of photons on the beam splitter, is used in creation of very unusual states of light and in many, many tests of quantum mechanics, and I'm hoping that with me talking a lot we will get thus far. And as you see as well, a simple beam splitter, a piece of glass with a little bit of metal on it, is amazingly powerful tool in looking at microscopic nature of our world. And I will be referring to it over and over again. So here I give you a... Yes, yes. Excuse me? I don't hear you. Oh, okay. Well, I'm not giving you this answer because you will be calculating it. This is your problem. So maybe I will ask you tomorrow. Right. But in order for you to be able to do it, I will actually tell you how to do it. First of all, here is our model of a beam splitter. We will represent it, I don't know if you can see it or not, I will refer to our input arms as A and B, and I committed a big crime here actually, and I hope you will not tell anyone, because I forgot to add an input B where I should place the vacuum state, which I told you just a moment ago never ever to forget. Anyway, from now on I will remember it. And here you are. So this is our model of a beam splitter. We have 2 inputs, and from each input, if we look, there is some probability of a photon being transmitted, some probability of a photon being reflected. We don't necessarily yet say what they are. And then we use so-called Heisenberg picture to propagate operators in time. So we are looking at, when you look at processes, the time variable processes, you have to either transform your variables or you have to transform your operators. In the Heisenberg picture, you transform your operators, and for beam splitters, this is typically what you do. So what we have here is this little matrix that tells me that if I have an operator A, I know what to do with photon states, having these operators, what is going to happen, how this operator is going to be transformed on the beam splitter. This will give me equations for these 2 operators, which I will know how to apply to the states of light. And by looking at various conservation rules, you can show that for a symmetric beam splitter, most of them, if not all of them, are symmetric. You can express it through this very nicely looking matrix, which only contains cosines and sines of some completely arbitrary angle phi. This angle is adjusted only to give you the correct ratio of transmission and reflection. So for example, if I want 50-50 beam splitter, of course I go for 45 degrees or pi4, because then both cosine and sine are 1 over square root of 2. This I appearing here tells you that there is a phase offset between transmitted and reflected light. Remember, we are talking about states, we are not talking about observables. So when you look at the probability of an event and you have to multiply by complex conjugate, this I will usually multiply to -1, and that's it. So here I also wanted to include something of semiconductor already, and this is a very modern looking beam splitter. Typically now, the reason we want to use semiconductors for optics, for quantum optics, is that we can make it compact. Typically, your beam splitter will be a cube of few millimeters at least, if not few centimeters. But that's not very convenient if you wanted to have a small device that you bring with you, or you have it in your future generation of mobile phone. Then you need something smaller. This scale bar is 2 microns. You can see the inputs to your beam splitter are these 2 waveguides. They are about 1 micron wide, and they go through the small membranes with holes etched into it. And the holes are etched in a very precise way that normally would be modeled numerically to assure that the transmission of a photon from this arm A into arm C or D is as you want it. This one looks symmetric enough that I would assume this is 50-50. And in fact, everything that I'm telling you about, and you know from your optics class, can be reproduced in semiconductors scaled down to the sizes where everything is within wave length of the photon that you are propagating. Now, going back to our maths, using this we will only work with 50-50 beam splitters. So using this matrix equation, I can now create my 2 equations that will tell me how creation operators on the input will transform into creation operators on the output. And here are the equations. This operators, the creation and annihilator operators, are complex conjugates of each other, and I'm pretty sure that it will be no trouble for you at all to derive them from this expression. If you know these 2 expressions, and you also remember what happens when we work with creation and annihilator operator on some Fock state n, then you are pretty much set to be able to know what happens with any input, what output you are going to get. So let's have a look at 2 simple examples. I leave the hard ones to you. So if I have m photons in arm A, n photons in arm B, for example, I will put 1 photon in arm A, I can always represent it as A dagger state 0, 0. A and B mark my 2 different modes. As you remember, these modes are independent. I can operate on them at any order I want. So you can really think about each of them separately until the point where they meet at the beam splitter. At this point, they are not separate anymore. If they have the same energy, if they have the same polarization, if I cannot distinguish one from the other, now that I also put them in the same place in space, I have to treat them as one mode. Before that, I can distinguish them by the arm of the beam splitter, and they are still not the same mode. But now we have only one, so life is easy. And here what I do. So I take this input state, and I use this equation to replace my A dagger, my operator on the output, with the 2 operators of the output. And I'm acting on this mode, which has been also transformed as AB into CD because of the way I wrote this matrix. And now I'm simply operating with the C dagger on this 0, 0 mode and with the ID dagger on this mode. And what I get, I had a photon from the first expression, I get a photon in arm C. And from the second expression, I have a photon on arm D. So I reproduced what we already thought. There is equal chance that photon will go into one arm or another. And here is a small example. What would I do if I had more photons? Let's say that I had 2 photons in arm A and 1 photon in arm B. Then I would express them as A dagger, B dagger, 0, 0. And I would use these equations as many times as I need to to convert into my output. Again, I'm not doing it because you are going to be doing it during the problems with our help, but it's not that difficult. And here, very important thing is to remember about these prefactors in these expressions. Otherwise, you will find that you have more or less photons than you put in on your output if you forget these factors. So when you do all your calculations and you add up probabilities of all the photons on your output and you find it's only 50%, then you know you forgot this number. So it's actually very pleasant to play with these numbers because you will suddenly find, of course, you don't want to do it for 20 photons. It's a lot of work and easy to make a mistake. But it's actually quite fun to see how suddenly you can create all these very strange outputs on your beam splitter that you would never think about before. So anyway, this is to show you that these states are really very strange, but it's, of course, sort of just observation. And we would like to be able to distinguish between classical states of light and quantum states of light. And it turns out not really. How would you do that? Yes and no. Again, in your exercises, you will find examples why it won't work. Because this is really an interference effect, what you have. You see, you had this I number here. This I number with a phase shift means that there are occasions where when you adjust the inputs in a special way, there will be an event of annihilation that your classical statistic would not predict. So I think classically, if you think classically, you would be thinking about adding intensities of photons, intensities of your light beam. Here you have to really think about interference effects. So rather, if you wanted to go for the wave expression, this would be adding electric fields, not intensities. But the answer is no, you can't. And you will see example where it would fail. Mm-hmm. Okay, you are all going forward to future. Yes, I will be telling, there are occasions where you can generate entangled photons, and I will come to it a bit later. These two are not yet entangled. If you, well, even if they were to be entangled, we wouldn't actually have any measure of this entanglement because we need some property to be, we need a property that we can measure to prove an entanglement. And I will show you later that you can create entangled photons by just putting two photons on the beam splitter. Okay. Right. So, how do we find if state of light is classical or quantum or non-classical? This is actually a very confusing concept, and there are many people working on optoelectronic devices that use a term not classical, non-classical light source lightly, meaning not knowing what they are talking about. There are very specific rules of what we call non-classical light. And it turns out that we can use second-order correlation function to distinguish between them. So what is a correlation function? Any correlation function is basically some function which looks at, well, I would have to use the word correlation again, between two signals, either in time or in space. And in this case, the second-order correlation functions means that we are correlating intensities of light. First-order correlation function correlates electric fields of the beam. And this is a classic interference effect. If you look at the Young slit experiments, etc., this is measuring first-order correlation function. Unfortunately, this particular function does not distinguish between classical and non-classical light sources. The output is pretty much always the same and only depends on the coherence length. However, this intensity correlation function can easily distinguish between the two cases. And what it what it really reads is that we are looking at what is the probability that we will have certain intensity of light at some time t plus tau if we measure certain intensity at time t. And to make life easy, we normalize it. This way everything scales from 0 to 1 or not, but it scales to some number, and we can compare one source to another. So this is the classical version of it, but as you remember, I never mentioned word intensity in the sense of quantum, so let's now convert it into our quantum picture. To do that, we link our intensity to electric field, and I think it's also something that you are very familiar with, that intensity of light is proportional to this product of electric field and its complex conjugate. In our case, it would be actually E plus and E minus. And if you do that, you end up with this expression that looks rather long, but it's relatively simple. So these are our E's, these are our E stars, and this is our intensity. And then we also use this particular expression that links electric field to our, in this case, lowering operator. The rest, as you see, is pretty much a constant. We can use that as a constant. This is electric field amplitude, polarization. Since we are discussing the same mode, it will all cancel out, and we end up with this very simple formula given here. So you see that second-order correlation function can be expressed through our rising and lowering operators. And how do we measure? We use beam splitter. That's why I will use this word. Probably you can count. This is going to be a clear winner. So in order to measure it, we put a beam splitter. We put light that we want to test on one input. The other one contains vacuum. And we have two detectors. And the experiment we perform is the following. We start measurement whenever the detector in arm, which I called before C, I think, D1. If detector D1 detects a photon, I start a clock. And I stop the clock when there is a photon in detector D2. And this way, I'm going to build a correlation of arrival times that will be related to the intensity of light. And now we can look at it from statistical point of view. So yet again, here is a reminder of this correlation function. We are looking at what is the probability that I will have certain intensity at time t plus tau if I have certain intensity at time t. And classically, you will find that G2 at time 0, it has to be bigger or equal 1. What does it mean, G2 of 0? Tau is equal 0. So what I'm saying that the mean of the E squared divided by E mean squared has to be bigger than 1. And if you remember how you do experiments and you are asked to calculate errors, you will be very familiar with these two inequalities that I'm writing here. Looking here, what do we really have? I have intensity of light that I measure at time t, mean intensity that I measure over a certain amount of time. I square it, and I'm saying that this particular quantity cannot be smaller than 0. And I think it's fairly obvious. First of all, it's a square of a number, so unlikely to be 0. Second, remember, whenever you measure something, there is a noise. And if you take a mean and you look at the distance between the real measurements and your mean, you will end up with something that is pretty much always bigger than 0. And then when you expand this bracket, you will find that what it means that the average value of squared I, square of intensity, is going to be bigger or equal square of the mean intensity. And that, plugged into this equation with tau equals 0, gives you this condition. So we now know that classical light will have to have the correlation, second-order correlation at time 0 bigger than or equal 1. And it is equal 1 for lasers. Lasers are a very specific state of light. There is coherent superposition of Fock states, and in quantum optics, this is considered to be the best representation of classical light you can have. And thermal light, sunlight will have actually value that reaches values of 2. Well, actually sunlight, yes, will have value of 2 at t equals 0. So here you see also on this graph where here we have our tau and here we have second order correlation function. You can see that I drew a line already for single photon source. So it's a Fock state, it's a number state with exactly 1 photon. And I show that this is equal to 0. And of course it's a little bit disconcerting because of everything I told you here. But it is the case, and that's what we measure. That's how we know this is non-classical light source. But before I go to that, there is one more inequality that I am not going to derive, but there is a second condition for light to be classical, and that is that G2, value of this correlation at time 0, has to be bigger or equal to value of the correlation at longer times. This is called Cauchy-Schwarz inequality, and whenever one of these two inequalities is not fulfilled, light is non-classical. So we have two conditions for light being non-classical. And here I show you an example for bunched, coherent, and anti-bunch light, where bunch light, you see G2 at time 0 is bigger than 1. It's a representation of our thermal light. And what it means that light tends to, photons tend to cluster. They tend to come in a packet, which means that whenever I detect a photon at time 0, the next one is very likely to come very close to it. Coherent light, laser light, is a perfectly random light. The distribution of photons in time obeys Poisson distribution. And there is a very strong link between statistics and quantum optics or quantum mechanics, in fact. So as I say, coherent light is our Poissonian distribution. And here, at the very bottom, I'm showing actually a single perfect Fock state. Photons come in a regular train separated by exactly the same amount of time. And finally, if you can see it, here's a little mathematical explanation or mathematical proof that single photon source will produce G2 as at time 0 equals 0. So you remember that first of all, if we go page back, oh no, it's going to be too painful. If you look at the very center, this is now our correlation function at tau equals 0. And I've done something else in here. I said my light source is steady, so time t also doesn't matter. It's not the light that I just switched on and it's still reaching its steady state. The light is on for a very long time and it's the same at time t, at time twice t, etc., etc. So I can get rid of t and I'm getting rid of tau because I'm calculating G2 at time equals 0. So now I take this group of operators and I'm operating on single photon source with it. And here are some of our rules. If I take our annihilator operator and I operate at state 1, I'm going to remove 1 photon. I ended up with 0 photons. You might also recognize that the middle A dagger A is nothing else but the number operator. If I now operate with this number operator and start at 0 state, I mentioned I'm going to get, no, this is wrong. I'm going to get 1 out of it. Let's go back and check. Where have I done, where is the mistake? I will have to redo it. So if I operate with this on 0, I'm going to get, no, on 0 I would have to end up with -1, I'm sorry, which we cannot do. So as you see, I also prefer to have the equations in hand. So this is 0. Yes, yes. Sorry? Yes, yes, it is. Sorry, it's a funny angle, and then that's what happens. I look at it from the angle, and sometimes I don't see what I see. Anyway, so you see now formally that any single photon source will produce G2 0. And you have the very big gap here to fill. And actually, one of your exercises would be to tell me what would be the highest value of G2 at time 0 that I would experimentally be able to say I'm looking at single photon source. Because you know, when you do experiment, it's very unlikely that you are going to be measuring 0. There will be some stray light coming from somewhere. In the end, we do eliminate light as much as we can. Detectors are imperfect. They might produce some noise. So I need to have a little bit more practical rule than G2 at time 0 equals 0. And here are some examples of measured G2 values of single photon sources. And you can see here, for example, it reaches maybe, if this is 1, it reaches something like 0.2, yet we are happy. This is single photon source. This was an experiment done in 2002. Another experiment, and this is on indium arsenide quantum dots in gallium arsenide that I would like to tell you about, but I'm slow. And this is another one on so-called NV- centers in diamond. Again, this value is about 0.25, and we are still very happy to believe this person that this is single photon source. So tomorrow you will tell me why we are so happy, why we can be so happy. All right. So as I told you, all that I've told you about until now is not really necessarily very new, and we don't need semiconductors for it. Atomic physics has been way ahead of us in terms of doing very fundamental, very interesting quantum optics. But semiconductors come in whenever there is an application to grab. And as I said, quantum optics was actually a subfield of physics that was a test bed of fundamental quantum mechanics. That's why perhaps because it's so easy with this beam splitter, but it was really effective. However, now in 1984, there has been a proposal of using quantum states of light to secure communication on the internet or over networks. And that triggered the entire field of semiconductor physics, which is very close to engineering, very close to electronic industry, to work very hard to produce single photon sources, which we would be able to actually turn into applications, turn into something that you can buy and secure your communication with your bank or with your friend or whoever else. Following that was a concept of creating quantum networks. If I have 2 quantum computers and I am able to connect them with a quantum state of light, I have twice as large quantum computer. If I only have classical connection, then I have 2 smaller quantum computers. Also, I'm actually able to do my calculations on this quantum computer remotely without revealing any information to anyone. I can sit in my office, I can sit in my living room, I can do my calculations of something very secret. No one will know what I am doing, provided that I can send this quantum state of light. And finally, metrology. It turns out that if I connect many satellites with quantum links, I can build a huge Michelson interferometer which will have unprecedented resolutions, spatial resolution. All I need are the sources, and they are not as easy as it sounds. So perhaps today I will have enough time to present you with this particular paper that triggered the entire field. This is a paper that has been presented on the conference of IEEE in India in 1984, written by Charles Bennett and Giles Brassard from IBM. Tells you immediately that we are talking about applications, and he proposed using single photons to code information that you are sending over network. The way it works is as follows. Alice is always the person who sends the information, Bob is always the one who receives it, and no one knows why Eve is always the one who is trying to intercept, but there you are. So what Alice does, Alice decides on some quantum bits, and these are zeros and ones. I think we all know that information are zeros and ones. these random bits are then coded either in two polarization bases. So I should add that it's polarization state of the photon that carries information. And so she decides on her zeros and ones, and she says, for example, I had the table before, she says the following, that my bit 1 can be either vertical polarization in horizontal vertical polarization basis, so really electric field vertical or horizontal, but it could also be diagonal if she codes in this diagonal anti-diagonal basis. We are really talking about direction of electric field, nothing more than that. So that's what she does. So she selects the basis, completely random. The randomness is a very important factor. If it is not random, someone can predict the pattern and use it to their advantage. So this is a very big factor here. Next one, photon. Alice sends the photons, and Bob receives them. Bob has to do exactly the same thing as Alice did. He has to decide on basis he's going to use to measure them. He doesn't know how Alice actually coded them, so he also chooses it in random. And these are the bits that he received. There will be some losses on optical fiber because some photons will be scattered, they will change energy. He will not receive them. After Bob does the measurement, he has to communicate with Alice on the phone or on classical channel to tell her how he chose his bases. Alice tells him which of them were correct. When they were correct, he can now select the bits which they share. They both know that they have the same bit, or they at least should know about it. So if there is no, this of course is the case if there is no eavesdropping. They are still not sure if there was eavesdropping or not. They only know that if there was no eavesdropping, they should have the same photon. So he selects some of them and communicates them to Alice. If it turns out that they agree with at least 50% accuracy or more than that, then they know there was no one who read the information. Because you know very well in quantum mechanics what happens, measurement pretty much changes the state of a particle. So if managed to measure some of the photons, she will have to do what Bob did. She would have to decide which basis she is using. She would have to take the measurements. In 50% of time, she would choose wrong basis, and then she would change the state of the photon. And if Bob now finds that he has higher disagreement between his measurements and Alice than expected statistically, he knows that Eve read the information. So this way, Alice and Bob are able, by comparing the sum of the qubits that they both have, they are able to say if someone read the photons on the way between them or not. If they agree that no one read the information, they have some key that they can use to code the information. However, if they find that someone must have read the qubits, then they have to abandon the key and try again. So the important thing to note here is that in quantum key distribution, you cannot stop anyone from reading the qubits that you are sending, but you will know about it, you will detect it. That's the basis of quantum key distribution, which is very different from classical case where you never know what happened. And so this was the beginning of the big field, and people got wild and said, well, there must be better method of coding information, there must be better methods of securing information. And indeed, people decided that an entanglement is a fantastic resource that one can use for sharing information between two parties. And I'm not sure how much time I have, if I should start or leave it. 2 minutes. Do you think we can do it in 2 minutes? I can start and we'll finish tomorrow. So entanglement is a property of quantum mechanical systems, and it's actually a very common property of nature. The big thing here is that we are starting to use it. And entanglement can be represented by this little blue box here. I'm saying that if I have a wave function that represents a wave function of few particles, I cannot separate it into a product of wave functions of individual particles. That is very much what entanglement is. And we had a question earlier today if a state from the beam that emerged from the beam splitter was a entangled state or not. And I said we'll talk about it later. And here you have 4 states, entangled state of photons that can be generated on the beam splitter. The entanglement here is entanglement of polarization. They have these special names. This is they differ in symmetry. We have plus and minus, and they also differ in polarization being the same in 2 arms of the beam splitter or different in the 2 beam splitters. And I'm going to show you now that there is a condition that allows you to distinguish between entangled state or only strongly correlated one. And that is not something I can do in 2 minutes. So we'll have to delay it until tomorrow. However, of course, I will show you that we are going to do it using a beam splitter and some detectors. So I think I will stop at this point and we'll resume tomorrow.
Okay, so we have time for a few questions. So, any questions? There's one in the back.
Thanks. I was pretty confused by the slide where you introduced the correlation measure, because from what I understand, your correlation is usually normalized by the variance and not by the squared mean. Because no?
No, it's normally normalized by square mean.
But if we normalize like this, I can think of a signal that has like a 0 mean and variance different from 0, and then it's not a number between 0 and 1, is it?
Well, variance is probably even less predictable.
I don't understand.
Variance would be even less predictable than mean. If you say mean 0, it means I have no light, and then I don't worry about correlation.
No, okay, but still, I can imagine a signal that has a higher variance than mean.
Correct.
And then this is not normalized between 0 and 1, is it?
No, it's not correct. You see, for chaotic light, it's more than 2. That's why I confused you. I know at some point I said it's normalized between 0 and 1. I shouldn't have said normalized. It's normalized by mean, but it doesn't have to be normalized between 0 and 1. So my mistake.
Okay, thanks.
It's normalized in the sense that at very long time, any light, any character of light, it will always tend to 1. But indeed, that was me misleading you. So by normalizing, what I mean is that if you take light that has certain intensity and twice as high intensity, if you didn't normalize it by its mean, you will end up with having different value of this correlation function. But if you divide by the intensity, then they will all collapse on the same curve. So you can imagine thermal light, or you can imagine laser light. Let's say laser light which has 1 microwatt of power, and laser light that has 2 microwatts of power. If I didn't normalize by mean, one of them would be at this level somewhere here, another one would be twice as high. And you wouldn't be sure if it is the same thing or not. If you divide by the 2 microwatts squared, 1 microwatt, they will collapse on the same curve. So.
Okay, for the next question, we have one from Gaza. So let me see if we have our connection. Okay, hello, Gaza. Can we hear your question now?
Hello, thank you. Yeah, first, thank you so much for thank you so much for your very interesting presentation. That's very close for our classes here for quantum and optics. So the students are very, very interesting to hear this presentation. Now, one of our students will ask you one question. Can you please hear for it?
Mhm.
Yeah, hi.
Hi.
Doctor. I'm sure science is quantum optics and quantum applications, such as quantum computing. And really, I want to follow my studies in this section. My question is that is it correct? Is it correct that there is no entanglement process without human intervention, without making anything in the laboratory, such as neon light or something? Is that entanglement process measuring in the net without making anything in the laboratory?
So let me repeat your question for everyone, if I understood it correctly. Your question was, is there entanglement naturally present in nature without making anything in the laboratory? Is that correct? Is that your question? Hello? Sorry, can you hear us? Yeah. Well, was that the right question? If there's entanglement present in nature, not in the laboratory? Okay.
The answer is yes. Entanglement is part of nature. I think what is happening now that we are learning how to use it, how to treat it as a resource. But if you are interested, what I can do, I can show you tomorrow, for example, how a certain polarization of light that is emitted by certain materials originates from entanglement present in the system. So yes, we are now pretty much at the stage where we are engineering the system. We are taking what nature is giving us in a certain way, and learning how to handle it. So that would be an additional slide for tomorrow.
Great, thank you. Any more questions from either side? Questions? Okay. In that case, let's thank Professor Beata again.
Thank you.
Okay, so that is the official end of the first day. So you made it. Well done. Okay, yeah, sure. Okay, and now a few more practical things. Tomorrow we will start earlier. We're going to start at 9 in the morning is the first lecture, so everyone should be here at 9. Tomorrow there's a lot of things happening. As I mentioned, there's the official lectures, there's the public lecture at 6 in Ramallah, and we'll provide some details on that tomorrow, the day of. And the dinner is tomorrow, also in the evening at 7:45. And finally, if you have accommodation that we are providing, then don't leave. Stay here, find us now, and we'll explain how that accommodation is going to work. Okay, thank you. Yeah. Oh, one more. Yeah.
If you haven't told me yet what you want to eat, let me know. Or if you've changed your mind or anything.
Okay, great. Thank you, everybody.